Hello friends, in this video we will do the integration part of the derivation of effect of temperature on Fermi distribution function. So this is completely relating to the mathematical part of the derivation. We have already considered the concept behind those portions, that derivation. Now we will just integrate one integral in that derivation. So first of all, in the derivation of the Fermi energy and its dependence on temperature, we had one integral from the equation for n, which is 4 pi v by h cube into 2m whole raised to 3 by 2 into integral 0 to infinity e raised to 1 by 2 dE divided by exponential e minus ef by kt plus 1. And for this integration, we choose this part to be integrated as I, and in the previous video we just substituted for this I by considering the final answer alone. Now in this video we will be integrating this factor using basic principles of mathematics. So now we have I and we need to integrate those terms. So to integrate this I, we will be using the product formula of integration, which is integral of product of two terms equal to first into integral of second minus integral of derivative of first into integral of second. That will be used. So to find this integral, we assume that 1 by exponential e minus ef by kt plus 1, this is our first function, and e raised to 1 by 2 is the second function. So what will be the integral value? Integration of products of two functions is first into, here the first term is 1 by exponential e minus ef by kt plus 1, first into integral of second. What is integral of second? E raised to 1 by 2 is the second term. Its integral is e raised to 3 by 2 divided by 3 by 2, and within the range 0 to infinity, minus integral derivative of first. So first function is this function 1 by exponential e minus ef by kt plus 1. What is the derivative of that function? What is the derivative of 1 by x? d by dx of 1 by x is minus 1 by x square. So this is a 1 by f of x function. So its derivative is minus 1 by exponential e minus ef by kt plus 1 the whole square into derivative of this factor, right? d by dx of 1 by 2x is minus 1 by x square into 2 into derivative of the function. So into derivative of exponential e minus ef by kt plus 1 is exponential e minus ef by kt. Derivative of 1 is 0. Now we have the derivative of the first function into integral of the second function. That will give you the complete second term. So integral of the second term is e raised to 3 by 2 divided by 3 by 2 into dE to complete the integration. So if you look here, in the first term, you have to substitute infinity and 0 into these terms to get the answer of the first term. In the second term, we are again we have again one more integral to do, and if we look into the first term, you can actually substitute 0 and infinity into these terms. But we know here the term that you see here, this term is f of e, right? And you know f of e for energy 0, probability is actually 0 because no electron can have 0 energy and no electron can have infinite energy as well. So the probability for 0 energy as well as infinite energy will both be 0. So we can conclude that this term will be just 0. So we are left with the rest of the terms alone. So let me modify that. So I is simply 2 by 3 into integral 0 to infinity. I actually made a small mistake here because the derivative of exponential e minus ef, the derivative of 1 by exponential e minus ef by kt plus 1 is minus 1 by x square into exponential e minus ef by kt into 1 by kt. That factor is also there because we have to again take the derivative of the factor within exponential factor. So into 1 by kt is also here. So please correct that. Now moving on, it is 2 by 3 kt into e raised to 3 by 2 into exponential e minus ef by kt divided by exponential e minus ef by kt plus 1 the whole square into kt, because that 1 by kt factor will be in the denominator. So we want to integrate this term here. Now before moving on, let us modify this integral in order to make it more easier to calculate. So first of all, we will be expanding this e raised to 3 by 2 terms as a Taylor series. Now what is a Taylor series? In a Taylor series, we will expand a function around one particular point. For example, f of x will be f of a plus x minus a into f dash of a plus x minus a the whole square divided by 2 factorial into f double dash of a plus etc. This is the Taylor series expansion for a function. Now what will be the Taylor series expansion for x raised to 3 by 2? If the function is x raised to 3 by 2 and if you need to expand this term around a, it will be a raised to 3 by 2 plus x minus a into f dash of a. Take the derivative of this term. What is the derivative of x raised to 3 by 2? It is 3 by 2 x raised to 1 by 2. And substitute a for x. That is how you calculate f dash of a. So f dash of a will be 3 by 2 a raised to 1 by 2. First calculate f dash of x, then substitute a for x plus x minus a the whole square divided by 2 factorial into f double dash of a. Once again take the derivative. What will be the derivative of f dash of x? F double dash of x will be 3 by 2 into 1 by 2 into x raised to 1 by 2 minus 1, which is 3 by 4 x raised to minus 1 by 2. So into 3 by 4 x raised to minus 1 by 2, a raised to minus 1 by 2, f double dash of a plus etc. So this is the Taylor series expansion of the function x raised to 3 by 2. Then similarly, the Taylor series expansion of e raised to 3 by 2 with respect to the point ef will be ef raised to 3 by 2 plus e minus ef into 3 by 2 EF raised to 1 by 2 plus E minus EF the whole square divided by 2 factorial, which is simply 2, into 3 by 4 into EF raised to minus 1 by 2 plus etc. This will be the Taylor series expansion for the function e raised to 3 by 2. Now substituting this Taylor series into the integral, we will obtain I equal to 2 by 3 kt. This kt factor is taken outside. 2 by 3 kt, all the constants are written together. 2 by 3 kt into integral 0 to infinity exponential e minus ef by kt divided by exponential e minus ef by kt plus 1 the whole square, and instead of e raised to 3 by 2 we are going to substitute this Taylor series. So into EF raised to 3 by 2 plus 3 by 2 into E minus EF into EF raised to 1 by 2 plus 3 by 8 into E minus EF the whole square into EF raised to minus 1 by 2 and so on plus etc. So this will be the integral. Now let us substitute for E minus EF by kt. Let us take this factor E minus EF by kt as simply x. So if we make this substitution E minus EF by kt equal to x, then what will be dE? dE will be kt into dx. kt into dx. So while doing this substitution, we also have to change the limits. When E is varying from 0 to infinity, what will be the variation of x? When E is 0, x is minus EF by kt, right? Substitute for E as 0, then we can obtain x as minus EF by kt. And when E is infinity, x will also be infinity. So when energy E ranges from 0 to infinity, x factor x will be ranging from minus EF by kt up to infinity. So if we substitute for E minus EF by kt as x, we should also change the limit as minus EF by kt up to infinity. Now this factor minus kt by EF, we know the graph of f of e for higher temperature is usually given as shown in this picture. So let me draw the graph. We have the x-axis marked with energy and the y-axis correspond to f of e, and even at higher temperature the f of e graph will look like up to somewhat length f of e will be constant 1, and after that f of e will fall. Maybe this will be EF value. So for a particular temperature, we can assume the shape of the f of e curve to be like this. And what will be the shape of the derivative of f of e? How will f dash of e look like? We know the change in f of e is happening only around a very small region around EF. Before that and after the point, f of e is constant. We know the derivative of f of e is a constant, and if you plot the function minus dou f by dou e, dou f of e by dou e, this value minus dou f by dou e will have values only around the range EF. So in this integration, we actually have to integrate 1 minus dou f by dou e factor, because we know f of e is 1 by exponential e minus ef by kt plus 1. So if this is f of e, what will be f dash of e? F dash of e will be minus 1 by exponential e minus ef by kt plus 1 the whole square into exponential e minus ef by kt into minus 1 by kt. This is the factor. So in the previous case, we actually had to substitute minus 1 by kt. This factor is plus 1 by kt itself. The derivative of e minus ef by kt is 1 by kt, right? I mistook that minus sign. So here again, this factor so this is 1 by kt itself plus 1 by kt. No change in the previous equation also. This is also 1 by kt. So we have f dash of e as this term minus 1 by x square, the function square into derivative of the function. And if you look into the derivative integration that we have to carry out, we can see that this term exponential e minus ef by kt divided by the function exponential e minus ef by kt plus 1 the whole square. This is simply the f dash of e, right? Avoiding the constants, we simply have f dash of e to be integrated. And this f dash of e, as I have already mentioned, has values only within a range around EF. So even if we integrate from minus EF by kt up to infinity, or if we integrate from minus infinity to infinity, the value will not change, because already we are integrating from minus kt by EF value up to infinity, and minus dou f by dou e is a function having value only around one small particular range. And if this integration is extended up to minus infinity to plus infinity, the final answer, which is the area under the curve, will not change. So instead of this limit minus ef by kt up to infinity, we will be choosing the limit minus infinity up to infinity. So finally, let me write I equal to 2 by 3 kt integral minus infinity up to infinity into e raised to x. Instead of e minus ef by kt, I am substituting x. How does 0 to infinity limit changed? Because first we substituted minus ef by kt, then due to the argument that minus dou f by dou e has value around only a short range, and the integration, changing the integration from minus infinity to plus infinity will not change the value, we change the limit as minus infinity to infinity. E raised to x divided by e raised to x plus 1 the whole square into ef raised to 3 by 2 plus 3 by 2 kt into x ef raised to 1 by 2, because E minus Ef will be ktx. Here we have E minus Ef. This term is now ktx into E raised to Ef raised to 1 by 2 plus 3 by 8 into kt the whole square into x square into Ef raised to minus 1 by 2 plus etc. into, for instead of dE we have to substitute kt dx, and this kt and the kt in the denominator will cancel out. This is a term in the numerator, and hence the kt in the denominator and numerator will cancel out. So finally we will have this is equal to 2 by 3 into, if we take Ef raised to 3 by 2 as a common term, Ef raised to 3 by 2 into integral minus infinity to plus infinity e raised to x divided by e raised to x plus 1 the whole square. This will be the first term. Now in the second term we have Ef raised to 1 by 2 and 3 by 2 kt as constant. 3 by 2 kt into Ef raised to 1 by 2 into integral minus infinity to plus infinity x e raised to x divided by e raised to x plus 1 the whole square. This is the second term. Now in the third term we have 3 by 8 kt the whole square into Ef raised to minus 1 by 2 as constant, and integration is integral minus infinity to plus infinity x square e raised to x divided by e raised to x plus 1 the whole square. These terms are common to all the terms inside the bracket into dx. So now we have to carry out all these integrations. So all these are standard integrals, and we can define the values of these standard integrals as integral minus infinity to infinity e raised to x dx divided by e raised to x plus 1 the whole square. Its value is actually 1. And integral minus infinity to plus infinity x e raised to x divided by e raised to x plus 1 the whole square dx is actually 0. And integral minus infinity to infinity x square e raised to x divided by e raised to x plus 1 the whole square dx is pi square by 3. So we can substitute for this integral with these constant values, and finally we will have I equal to 2 by 3 into Ef raised to 3 by 2 into Ef raised to 3 by 2 into 1 plus second term will be 0, right? This term will be 0 because the value of this integral is 0 into plus 0 plus 3 by 8 kt square, 3 by 8 into kt square into Ef raised to minus 1 by 2 multiplied by value of the integral. So it will be 3 by 8 into kt square into Ef raised to minus 1 by 2 multiplied by the integral value is pi square by 3. So solving this we can find 2 by 3 into taking Ef raised to 3 by 2 as common, (2 by 3) into Ef raised to 3 by 2 into 1 plus, in the first term only 1 will be left, and if we take EF raised to 3 by 2 from here, it will be EF raised to minus 1 by 2, again a minus 3 by 2, right? What will be that? It will be EF raised to minus 2. So that term will be simply pi square by 8, because these 3 and 3 in the denominator will cancel out. So pi square by 8 into kT by EF the whole square. EF raised to minus 1 by 2, the minus 3 by 2 term will be 1 by EF square. So this is the final value of the integral, and we will be substituting this integral into our derivation to calculate n. So n will be finally 4 pi v by h cube into 2m whole raised to 3 by 2 into I, and the value of I is as derived in this mathematical part. I hope you understood this derivation. Thank you.